Awesome. Hello, everyone. I see folks have joined and are still joining. Um, my name is MK. I am the Project Resource Mobilization here at Num Focus. Welcome to PyData Global 2025. Today's session that you are joining us is called Scaling Fuzzy Product Matching with BM25, a comparative study of Python and database solutions. Our speaker today will be Aniket, who is an engineer at heart. Aniket has founded Curlscape, where he helps businesses bring practical AI applications to life fast. He has led the design and deployment of large-scale systems across industries, from finance and healthcare to education and logistics. His work spans large language models based information extraction, agentic workflows, voice assistants, and continuous evaluations frameworks. So we have some exciting things to learn from Ankit today. And everyone, let's welcome Ankit to the stage by give us some emojis, some hand claps, some support. Welcome, Ankit.
Thank you. All right. So today we'll try to see how we can scale uh, fuzzy matching and search with BM25. Um, so I'm going to share the case study today. So a bit about me. I think we've covered this part. Thanks for the kind introduction there. So essentially, we help at Curlscape. What we do is we help solve complex data and AI problems, right? And that's what we do essentially. This is a case study of one of the use cases that we had um, that we tried to solve, right? So the challenge was this. Uh, in this case, we had 1 million, approximately 1 million food product records. And by food product records, what I mean is essentially these were ingredients, allergen information, nutrition information collected from various sources. And there were just 1 million of those records that we had. Uh, and the challenge was that, and it spanned approximately 2 GB. Just to give you some rough sense of how much the data is, uh, we had another set of reference data sets, mainly open food facts and FDA data sets. Uh, Open food facts, OFF, that we had roughly had approximately 3.8 to 4 million, and uncompressed on TSV, it would occupy something like 11 GB space. That's the amount of data that they had. It's, by the way, a community sourced essentially, and it's free to be downloaded. And we had FDA data set as well, which is community driven and freely available to download. So that scale was also in the million scale. Now, essentially, what we had to do was take the data from these reference data sets and enrich information from here into the target data set that we had, right? That was the problem statement. But the twist was that we didn't have an exact match in terms of the product names, right? Uh, we'll see some more examples coming up, but essentially we had to there is no shared identifiers because obviously the data sets are different, so you don't have id to id matching in this case. The naming conventions themselves are different, and the only way that we could do is take the names of the products from the two data sets and somehow find a way to match them 1:1, right? Now, to achieve this goal, um, this essentially was a m cross n problem, right? We've got 1 million products on one side, approximately four-ish million products on the other side that we've got to match. So, so approximately to match that 1 million, even if you, let's say, do that in a second's job, uh, let's say 1 million products, each product search takes, let's say, 1 second to complete. it would roughly take approximately 10 days per data set to complete this job, right? Now, as I said, we had two data sets, OFF and FDA, and we didn't have 10 days. So uh, the target timeline we wanted to get to is something like a day basically. And if we get to a target latency of something like 100 milliseconds per search, we would be able to do this, right? So what we needed was a sub-second search per query, and an index-based retrieval, uh, not brute force, obviously, because you see 1 million cross 4 million, it's a m cross n problem, doesn't scale. It has to be fuzzy matching, so uh, it cannot be an exact match. And a lot of libraries exist in Python as well, which help us do this fuzzy matching, but it has to be a bit more sophisticated, uh, and also scalable with respect to the whole enrichment part of it. I'll probably talk about that in a couple of slides down the line, right? Now, here are some examples of these products that we had, right? Our data, and this is some delicious Turkish coffee, I'm told, by the way. So this is the title of the product that we had. Same product exists in Open Food Facts, but the name obviously is different. If you see the product within Open Food Facts misses some of the key details there. Um, Things like the type of beans, the type of aroma. I mean, some of the products have got the some of these attributes in the title just so that they can advertise that better. Some of the products even had extra information, things like measurements, like units and things like that, packing information. All those things were added in our dataset. Now, the uh, the trend is similar. So in some products we had the names shorter, and in Open Food Facts the product name is larger, and so on. So that would be this is an example of the problem that we are dealing with. The other problem that we had was we wanted to, in some sense, have a search that essentially takes into account the word order, right? Reduced fat milk, 2% versus 2% reduced fat milk. You see, the content is same, but if you go ahead and match these, obviously we'll not have a one-to-one matching around it. So semantically, they mean the same thing, but while matching it becomes a challenge. Extra information, as I said, some of the titles contained more information. Spellings, right? Big challenge. Some people spell Coca-Cola like this, with a hyphen in between. Some people do not add a hyphen in the spelling, so it could be a challenge. Units as well. Uh, Although the value themselves are similar, but you would see the nightmare with the units, and hence it becomes challenge. Although we didn't actually solve the units challenge at this point in time, but this talks about the overall challenges that we had. So we needed something that we could use. We could use that essentially searches across the product names within by keeping in mind the semantic essence of the product. Uh, Enter BM25. BM25 is a search engine, or I would say an algorithm that basically doesn't do a string to string match. The way it works is essentially BM25 works as it reads the text documents as backup words, right? And essentially, what we try to do is we try to come up with a score, and that score is something that is used to match given two sets of products. And we sort the scores, and based on the scores we try to find out for a given text which other text comes very close to it based by looking at the scores, right? um, some of the attributes of BM25 is that it basically takes into account rare words and uh, treats them properly. So, for example, some of these unique names uh, which appear in the text, they are given high importance compared to more commonly appearing terms such as words like coffee, words like milk, things like that, which are more commonly appearing. So it tries to give importance to those. The word order doesn't matter in BM25, so it makes sure that whenever you're searching, you can be searching for Turkish coffee Fendi, and your target could contain Fendi Turkish coffee. It doesn't matter. BM25 matches them perfectly, right? Extra words are okay, so it doesn't uh, like punish the extra words being added into the names, or rather strings. Document length is also normalized. Compared to TF-IDF, this works a little differently. So in TF-IDF, if coffee appears 100 times, then TF-IDF does not normalize for the IDF, but essentially BM25, uh, even if the word coffee is repeated multiple times, the score kind of gets saturated beyond a given term frequency. Now that is helpful because you wouldn't want to like overemphasize on certain words appearing 100 times. So coffee appearing 100 times doesn't make that particular string better or have more score or higher score essentially. So it was decided that BM25 is the go-to search in this case. So we went ahead with that. The way BM25 works is that here is how we calculate BM25. Here, in this particular formula, uh, f of q given d is essentially denotes the number of times that the keyword q has appeared in a document d, which has essentially d words in them. uh, and basically it punishes the I mean it has a component of term frequency and inverse doc frequency, but it also normalizes the length for it. These parameters here, k1 and k2, sorry, k1 and b, are found to be typically working in most of the scenarios, and we generally do not find it the need to essentially tune them essentially, right? Uh, the best part is that uh, the way BM25 works is that you have to index the whole data set once, which means that if I've got open food facts, I index that particular data set once and I store the index. And next time onwards, I just reuse that particular index and search on top of that particular index. I don't need to index it every time, right? That's how BM25 works. Uh, so yeah, we started with BM25. Rank BM25 happens to be the implementation here. There is a nice library in Python for this, and we ended up using it. The way you use that is, I mean, there's a short pseudocode provided here, and we get top k as the search that we get. Um, Obviously, this didn't solve the problem for us because the overall latency that we had was somewhere around 90 to 120 seconds per query. Very, very high, right? For a 1 million set of products, this was literally unusable for us. The reason why it was slow is because we had pure Python loops in those, and the complexity was n log n, and it had to sort for the top k retrieved products, and hence it was very slow. Pure Python loops, we know that it is slow. So obviously, it was not the solution that was going to work for us. Uh, the next thing we tried was DuckDB, and the nice thing about DuckDB is that you first of all it is SQL like. So uh, first you load your data set and you create your index using uh, the full text search plugin inside DuckDB, and you can also specify the stemmer and stop words. So stemming is a method wherein what it helps to do is it helps to remove the extra prefixes and suffixes from the words, which makes the BM25 search very fast as well as efficient. It also helps to remove the stop words, and we can also specify what language that we are dealing with. And essentially, DuckDB helps us to do that. It has got inbuilt way of adding a stemmer and removing the stop words. We tried this, and in this case, first of all, the problem with this is that the very high memory usage. So for approximately 3.8 million products, we had a memory footprint of something like 20 to 30 GB, and the latency for that as well was something like zero point 0.3 to zero point 0.5 seconds. It was better than the naive approach of BM25, yes, but still this kind of latency was not useful, because if we take a look at the original numbers, assuming 1 second, it takes 11 days. Assuming 0.5 seconds, it takes 5 days for one data set. Not acceptable, right? Some of the nice things is that it doesn't have Python dependencies. Everything is sort of in one package and easy to integrate and do analytics on top of it. DuckDB has got so many other things which are nice to use. So in those sense, it was useful, but not for doing BM25 itself, essentially. Uh, the breakthrough was when we tried this library called BM25S. Uh, there is a nice GitHub repository for this. The link is right here. If you search for this, there's a BM25 implementation of this algorithm provided in the repo. Uh, the What it makes is it so fast is that they use the SciPy sparse matrices, and at the time of indexing, we kind of pre-compute the scores, and we are able to reduce the complexity to from n log n to n, and that way the latency becomes better. Uh, the It also comes with a stemmer uh, uh, added with it, and essentially we first import the stemmer. We initialize that with English. We compute the tokens and remove the stop words, create the BM25 index, and we essentially store the index for query next time. With this, the query latency came to 50 to 80 milliseconds, which was very acceptable and very amenable to our use case that we had. And with this, we were able to search for millions of products very fast. Right now, let's take a bit of deep dive into understanding what is it that that makes this BM25S fast. Right. Essentially, what happens is that in the traditional BM25 algorithm, what we do is at the query time for every document that we have, we essentially compute the score by computing the term frequency and inverse document frequency, which is very inefficient because we are doing it at the query time. As opposed to that, what BM25S does is that at the index time, it pre-computes the scores, and it stores that as sparse matrices in the index itself. So at the query time, what we're trying to do is we're trying to just slice and dice across the matrices that we have, and that makes it very, very fast, right? So when the that makes it better, and there is a bit more of algorithmic complexity here. So essentially, assuming that we've got 50,000 unique tokens in our overall corpus that we've got. The overall corpus here is the 4 million sets of documents that we've got. Every document here is a string. So that's the corpus that we are dealing with. Now, the key insight here is that we are not going to find that we are not going to find every token in that particular corpus in the target token that we have got. So that's one thing that makes this very, very fast. So at the first of all, at the index time, what it does is that it creates a dictionary of terms with their frequencies, um, and that mapping of terms with their frequencies is stored, and essentially it's stored in the index, right? And at the query time, based on what the query string is, it essentially does the lookup for those strings after we do the stemming as well as stop word removal. Hence, the lookup essentially only gets restricted to the number of tokens that we have got in the string itself of the query, right? So, for example, if you've got Turkish coffee as the string that we are trying to look up, then we would have only two lookups in total for that particular query, right? Also, as I said earlier, we are going. This particular library uses sparse matrices to store the information. The reason why that helps is because when we store the information in, I mean, when we store the matrix in sparse format, which are especially for the matrices which are sparse in nature, the amount of information contained there is very small. And if we treat it as sparse matrix, then we are really saving up on memory as well as uh, compute, basically. At the time of uh, computing the index, then uh, basically the slice operation that happens at the query time needs only the tokens from that appear in the query, and hence the computation reduces significantly. So after this slicing, basically, in the end, we compute the scores for these, and essentially we find the top n scores which appear in the dataset, and we essentially rearrange all the strings that we have got to find out the top n, and we find out the and we return those scores. In this case, for the data set that we have got, uh, we we uh, we use token IDs. That's how it works. It handles the tokens in the background using arrays, which are contiguous memory blocks in the memory. And also, because of the sparsity handling, it only stores non-zero values, as I said. Uh, BM25S essentially took approximately 2 GB of memory on uh, 4 million documents, which was very, very easy and handy. You could run it on a laptop essentially. And lastly, the memory mapping functionality is also available. So even if the dataset size increases to, let's say, 10, 20 million documents in the downstream, we know that we can handle that complexity using memory mapping by offloading the memory onto disk as well, right? So that was the overall strategy as to how we used PM25S. Uh, in the end, we obtained a speed up of from, let's say, 120 seconds all the way to 80 milliseconds. It was a huge speed up of 1500x for approximately 1 million queries. It took us approximately a day to get this done, versus let's say 11 days. That, I think, 3.8 years is a typo there, but approximately 11 days is what we could scale it down to 1 day. Okay, so the way it works is, the moment we enter our query, which is the product name in this case, the following products from Open Food Facts surface. So first of all, the first one is a product that matches very, very closely, because the I might be pronouncing this wrong, but Kurukavesi Mehmet Effendi is essentially appearing in both the strings, and that has got the highest score. But if you see the second one, the word order changes, still shows up in the results. And for the third one, we've got some extra information here in open food facts, still shows up there. So first of all, it was able to ignore the extra tokens that it has got, and reorder was taken care of as well. And it made sure that Kurkavesi, which is the name, has got a higher value because that term does not appear so frequently in a database. So this is the way that we ultimately sorted to enrich the products of 1 million that we have got from a set of 4 million products. And ultimately what we mapped were ingredients, nutrients, and allergens. This was, but this was only half part of the problem, because what BM25 gave us was how to identify a particular product that we were looking at from a set of, let's say, 4 million products. But we still had the data um wrangling issue of essentially loading the 1 million products for each product, searching them, searching for the ingredients, nutrients, and allergens from the 4 million set, joining them into the 1 million set, and then handling other business cases, which is handling missing values, null values, and things like that. We tried doing this in native pandas, but the, the requirement of memory and everything becomes very, very complex. We had two GPUs at hand at our disposal to try. Hence, we started exploring QDF and Task for this particular use case. And uh, what we essentially had was the results were very good. So with GPU based data loading and implementation with QDF, we essentially import the required packages. We then read the CSV as it's a normal Panda CSV. But the good thing about Dask QDF is that uh, it's an eager computation. So whenever we want to apply a particular operation onto a particular row, it gets computed at that time. Hence, it's sufficient with respect to memory. Here are some numbers, right? So with pandas, for CPU, this particular operation, the data loading operation itself took approximately 2.5 to 3 minutes. With GPU, that came down to 17 seconds, right? Uh, Approximately 14x speed up in data processing. Just to give you some idea of the hardware, we had Dell PowerEdge with 64 GB RAM and 24 core CPU, and it was connected to dual 3090 RTX GPUs. So basically, with this, we had best of both worlds. We had the goodness of BM25 accelerated, as well as usage of QDF as well. So the complete pipeline looked like this. So we loaded the data in QDF plus task, build the index, and search using batch, enrich it using QDF UDFs, which is GPU parallelized, and finally export the whole data set as a Parquet file. Uh, and we used 50 workers for this, and with a batch size of 500, um, per product was much less than 1 second, and overall time we achieved this in 6 hours. Uh, so some rough numbers is are here compared to the native implementation of Python. It We had at least 5000x speed up with this, and the match quality was approximately 85. The way this was calculated was we had we have a subset of data onto which we monitored what the ranking was basically. Um, Let me let me come to the last slide. Um, so one thing that we here are a couple of learnings that we have had, right? So first thing is that index persistence is essential. So the best thing with BM25S is that you build the index once, save it in a disk, read it when required. So that saved a lot of time. Stemming is non negotiable. Stemmer actually helps you to convert strings into amenable formats. Uh, Batch operations help. So dividing the whole operations into batches help. GPUs. So GPUs with QDF, we could accelerate the whole data processing workflows. And profile before you optimize. Essentially, it's best to first measure what works for you and optimize the slow processes. And algorithm choice. I think the algorithm choice matters more than the hardware. Okay, let me stop here and let me stop sharing the screen as well.
Thank you, Ankit. Let's everyone give a round of applause to our speaker, Ankit. And for those that are interested in continuing the conversation, we can continue that on Discord or Slack. And also, if you've attended or want to listen to this again, this recording will be made available, and any resources that are shared as part of this recording will also be attached to it. So thank you all for joining and hope to see you at the next session. Again, we can continue conversations on Discord or Slack.